So hello everybody. Now we are entering into the new week, week 5, and this week we'll be discussing about interesting set of compounds, particularly concerning the solid state. And now we'll be focusing our discussion on host guest interactions in compounds that form clathrates. So, clathrates is a new class of chemical entities, and the formation of clathrates is particularly in the solid state, because now what happens is that we have got the host molecule, which is not an individual molecule. Okay, it is not necessary that the host individually has to complex with the guest, but what is more important is that the host forms a three-dimensional lattice or a three-dimensional crystal structure. That is, it corresponds to a solid state where you have the host molecules arranged in a periodic fashion, and now this host framework either generates voids in the crystal structure into which I can include the guest molecules, for example solvents or other organic molecules or drug molecules, etc. And I can also have the host which has got different crystalline arrangements, and this phenomena by which a host molecule or any compound can exist in different crystalline arrangements is referred to as polymorphism. So we are now going to enter into the field of solid state inclusion complexes, solid state clathrates, formation of different crystalline forms of a given substance, which we refer to as polymorphism, solid state phenomena, crystal engineering, hydrogen bonding topology, how the hydrogen bonded frameworks form crystalline structures, and some of their applications. So this week is going to be a very interesting learning experience, where we will talk more about crystalline solids and host guest complexation behavior in solid state compounds. So now we can look at these different aspects of solid state arrangements of the host molecules in the presence of the guest molecules, where it is not a prerequisite for the host molecule to interact specifically with the guest. So what is the properties of clathrate? So in a clathrate, the host, I can write host molecule H, is the entire, usually this is crystalline, it's a crystalline compound. The host molecule is the entire, usually crystalline, is the entire solid, and the guest binding cavity need not be an intrinsic property of the individual host molecules. So when we are going to have a guest, it will specifically look for a cavity, and the cavity need not necessarily come from the host molecule, that is, it will not necessarily be the intrinsic host cavity, but the cavity can be created by the three-dimensional arrangement of the host molecules to form a three-dimensional solid, which we call a crystal, and that cavity which is created can now include guest, and hence this need not be an intrinsic property of the individual host molecule. Number 2, the composition of the clathrates need not be stoichiometric. There are voids which are present in the crystalline lattice which is created by the host molecules. It is not necessary that all the voids be occupied. Most of the voids will be occupied, but some will be statistically unoccupied, and that will result in the composition of the clatrate to be non-stoichiometric. So it is not necessary that the composition of the clatrate be stoichiometric, and this can happen because this is because it is not necessary that all the voids in the crystal are filled with gas. Okay. So we can have clatrates which are non-stoichiometric. This is because it is not necessary that all the voids have to be filled up with the gas. So keeping these two prerequisites in mind, and knowing that the parent molecule, that is the host, can actually create its own structure which can create a cavity, which not necessarily create a cavity. Depending upon whether it creates one, the guest binding molecules can go and now occupy the voids which are present in the crystal structure of the host molecule. Now let us look at these aspects of clathrate formation in a more general sense. So to start with, we have got a host molecule which is cavity free, and this host molecule, which does not have any guest included, does not have any cavity, forms a particular crystalline arrangement, is called the apohost. It is called the apohost. And normally this apohost is bulky, number one. It is a rigid structure. It is a very strong structure. It is a rigid structure. You cannot disrupt the crystalline lattice easily. So it is bulky and rigid. And number three, it contains specific functional groups that can hydrogen bond with the guest molecules. So it is necessary that we have some specifics here in terms of the functional groups which are present on the apohost, such that they can form strong hydrogen bond with the guest and form these clathrates. And now this is a solid, and we now add the guest molecules. We are considering the guest molecules to be liquid. Needless to say, you can always have a solid host plus a guest, which is a solid, liquid or gas, which is in equilibrium with the host guest complex, and the resulting host guest complex is a solid. So the gas can be solid, liquid, gas. To start with, my host is a solid state structure, and this can form a host gas complex which is a resulting solid and which has got high degree of crystallinity. So when we mix these guest molecules with the cavity free apohost, we have the solvation now. We know that now these are all swimming around here. So we now have the apohost which is being solvated by the liquid guest molecules, and then what can happen is that it can crystallize containing the guest molecules So now you can see a very nice three-dimensional structure is formed, where the arrangement of the apohost molecules, you can see here, is different from the cavity free. So this is the one which now contains the guest molecules along with the host molecules, and it forms a crystalline framework or a crystalline structure, where the guest molecules goes and occupies the voids which are created by the host molecule. So the host and the guest together create this three-dimensional structure. Now what can happen now is that once we get this host guest complex, we can try to remove the guest molecule and see what happens to the host structure. Either the host structure will remain the same, that means the crystallinity of the host structure or the host framework is maintained, or when you remove the guest molecules, the crystallinity can decrease, or there can be loss of crystallinity and the structure can collapse. That means the host structure will lose its parent arrangement, the entire three-dimensional structure will collapse. This is another thing which can happen. And the third thing which can happen is that when you remove you can remove some of the solvent molecules, but some of the solvent molecules still remain, and that creates another phase. So we can have another phase. For example, let us call this the beta phase. Let us call this the beta phase, and the cavity free is called the alpha phase. So now we can get a possibility of a third phase for this host guest complex. So let us look at all these three possibilities. So first of all, when you have the removal of G molecules, that means the guest molecules, you can get back the alpha phase, which is the apohost, plus the solvent molecules, the guest molecules, which are actually liquid in nature, will be released into the bulk. The next thing is that we can remove the guest molecules from the structure, and it will now be so now you see the apohost is formed. Again, this is a new apohost. This is a new structure which is actually a different crystalline arrangement than that of the alpha phase. This we call as the beta 0 phase. Again, this is a apohost, but this arrangement is different from this arrangement. So when you bring in the guest molecules, there is a change in the crystalline arrangement of the apophase, and now when you remove the guest molecules, it will have a different structure corresponding to a different arrangement of the apohost. So essentially this apohost or this particular beta 0 phase is derived from the beta phase by simple removal of the guest molecules. And you can have a gamma phase which is formed when you have a gamma phase where you remove some of the solvent molecules. Now when you remove some of the solvent molecules, you will have a different arrangement. Let us see that arrangement. So you will have the solvent molecule sitting here, the guest molecule sitting here, then you will again have the guest molecule sitting here, and you will again have the guest molecule sitting here, but you will have no guest molecule sitting between these. So you see this particular arrangement essentially happens because now what you have done, you have removed some of the solvent molecules, and therefore these two chains come close to each other and they pack themselves in a way so as to maximize the van der Waals interactions, and therefore we now get a new phase, the gamma phase, where some of the voids have been filled up, whereas some of the voids have lost the solvent molecules, and a structural rearrangement has taken place to give you a new phase which we call the gamma phase. So you can have cases where the parent host structure generates voids and all the voids are filled up. You can have removal of all the guest molecules, then all the voids are present, that is called the apohost, and we can also have partial removal of the solvent molecules and then some rearrangement in the structure so as to maximize the close packing and to minimize the voids, and the voids which were already occupied still have the guest molecules, giving you a gamma phase. So all these possibilities exist when you have the formation of clathrates, and today in the literature there are a large number of examples where large number of compounds have been made which actually crystallize first. Now the purpose of forming the solid state is important because the individual host guest interactions are not strong enough to enhance the binding, and because the overall binding is weak, because effectively these are the interactions between more like non-polar host and non-polar guest. So what we do is that we now essentially form the crystal structure, because now there is a network of hydrogen bonds which actually make the solid, and then the guest molecules which are in the liquid state can come and crystallize along with the host molecules in the three-dimensional structure. So we will be looking at examples pertaining to these clathrates, and in this regard we will first look at clathrate hydrates, okay, where essentially we have now got the formation of a hydrate structure, and the hydrate here refers to the water molecule. So water molecules here forms a three-dimensional structure, and here it is the entire three-dimensional structure which serves as a host, and these water molecules are strongly hydrogen bonded, and the overall cavity which is created by this three-dimensional structure of the water molecules can now include different kind of guest molecules. These guest molecules can be as simple as hydrogen, chlorine, bromine, iodine, hydrogen sulfide, HCN, chloroform, carbon tetrachloride, carbon disulfide, nitric oxide, carbon monoxide, carbon dioxide, alkanes, and so on and so forth. So all the spectrum of molecules can now be included as guests. So you can be included as guests in the structure of the host lattice. So water here, to start with, via extensive hydrogen bonding forms a three-dimensional structure. We have the OHO hydrogen bonds. Via extensive hydrogen bonding forms a 3D structure which is the host lattice, and the voids, or you can say the cavities which are created, can be now filled up with small non-polar guest molecules. For example, we can have chlorine, bromine, iodine, HCl, hydrogen, carbon monoxide, carbon dioxide, carbon sulfide, NO, etc. Plus, and very importantly, alkanes also. Small size alkanes, for example, methane, ethane, propane, butane. So all the spectrum of very small molecules can now be included in the host structure which is formed by extensive hydrogen bonding of the water molecules. So we call these clathrate hydrates, and these clathrate hydrates were first discovered in 1810. So I would like to give you some background to the history of the formation of clathrate hydrates, and then we will go to the structure and other related properties of these clathrate hydrates. So, and when you have the formation of these clathrate hydrates, the structural property for formation of clathrate hydrates is that there does not exist strong hydrogen bonding or dipole-dipole interactions between the host lattice and the guest molecules. This does not take place. There is not much a strong association between them. So, the first hydrate species was actually an aqueous solution of chlorine. An aqueous solution of chlorine gave a solid compound of composition Cl2.10 water, and this was first discovered by Sir Humphrey Davy in 1810. So, this was first discovered by Sir Humphrey Davy, and the composition was confirmed by Michael Faraday, a very famous scientist, in 1823. So, once the compound was discovered, the composition was confirmed by Michael Faraday, and it was found to be Cl2.10 water. Following this, a lot of research went on to the formation of these gas hydrates. We call these gas hydrates because Cl2 is a gas and water is a liquid, and water forms a structure into which we can have voids in which chlorine molecules can go and now occupy the voids created by the host lattice. Following this, SO2, that is sulfur dioxide, has been used as a guest molecule and complexed with hydrates to form the inclusion complexes, and this was done by de la Rive in 1829, followed by bromine as a guest molecule, the aqueous solution of which gave the Clathrates hydrate, discovered by Alexeyev in 1876. So, Alexeyev discovered this in 1876. And finally, the most important discovery happened when alkanes, example methane, formed gas hydrates, discovered by Willard in 1888, followed by the inclusion of noble gases. The inclusion of noble gases by de Forend in 1923. Inclusion of noble gases by de Forend in 1923. Now, so there were large number of discoveries which were done with respect to the formation of these gas hydrates, and the most important discovery turned out to be the combination of compounds which are formed by alkanes with these water molecules, and this turned out to be a very significant discovery. And before we go more further into why this discovery is important, I would like to now mention that these solid state clathrates are formed under very specific conditions of temperature and pressure. Okay, they are formed clathrates of the solid state type formed under very specific conditions of temperature and pressure. Particularly these are formed at low temperature conditions. Okay. And the next most important property of these gas hydrates, which distinguishes it from the solvent molecule. For example, here the molecule, solvent molecule here is water. So water has got its own set of properties. Water is a liquid at room temperature, and below 0 degree centigrade it freezes to ice. So the properties of this gas hydrate is very different from the properties of ice. And one such important property is the melting point of these clathrates, and it has been found that the melting point of these is 31.5 degree centigrade above the melting point of the hexagonal form of ice. Now ice, you know, when it is formed, depending upon the pressure and the temperature of the system, can form different type of polymorphs. In other words, you can have different crystalline arrangements of the water molecules in the ice structure, and in this case we are referring to the hexagonal form of ice whose melting point is 0 degree, and the melting point of this clathrates is actually 31.5 degree. That means these clathrates, which are actually the inclusion complexes of different nonpolar species with water, they are very stable. They are thermally very stable, and they melt at much higher temperatures compared to the temperature at which ice melts. And this is a very practical problem. Now why is this a practical? This is a practical problem. This is a practical problem because when alkanes, for example methane, ethane, propane, butane, you know, these kind of gases or natural gases are being transported. These are transported via pipelines from one place to another in cold conditions at low temperature. These block the transport of gases by forming clathrates or gas hydrates. So now you see you have got a pipeline and you are going to transport methane or these hydrocarbons. Now when the outside temperature is very cold, then and you have got moisture or water which is present inside these tubes, then what happens is that water combines with this methane to form gas hydrates, solid state structures, and now these essentially fill up the entire pipeline. So these form a solid inclusion complex. So methane plus water forms this solid state inclusion complex, where water has got a parent structure and methane gets included into the voids created by the structure of water, and these essentially have very high melting point. That means even when the temperature goes up to 10 degree, 15 degree or 20 degree outside, these blockages which are formed, these solid state inclusion compounds which are formed, they have completely blocked the passage of methane through these pipelines, because these gases have to be transported from one place to another under the seabed, and that process does not take place. Now once the blockage takes place and gases cannot be transported, then these blocks have to be removed. These blocks have to be removed. And it has also been observed that now when you take these gas hydrates and apply high temperature, these gas hydrates burn. And what is essentially burning in these, say you have these gas hydrates, and when you apply high temperature, you will see methane gas coming out and water being converted into vapor. So both water converts to vapor as well as the methane gas is being expelled, and this gas formation takes place, and the process leads to conversion of the solid state hydrates, solid state inclusion complexes into the corresponding gases. And this is a $1 million problem in the industry, because what happens is that these pipelines can burst, because if the gas hydrates are not removed, then the pressure builds up inside these pipelines, and this can lead to bursting of pipelines, and this can actually be quite devastating, and this can lead to severe losses because gases are being transported and these find applications. So this is a serious problem, the formation of gas hydrates, and the remedy to this gas hydrate problem is you can remove the gas hydrates, as I said, by applying high temperature, or that is by warming up, or putting a reagent that absorbs water or moisture, and therefore the methane gas will be released. That is one way of doing. And the second way is to add kinetic and thermodynamic inhibitors that do not permit formation of these clathrates. So we can add an inhibitor that prevents the formation of these hydrate-like or clathrates structures. So, so you see that this formation of gas hydrates is, or this particularly inclusion complexes with methane, ethane and all, is a serious problem, and this has to be treated, and this is one of the very important applications of these gas hydrates. Now what we will look at in the next lecture is to now look at the structures of these gas hydrates, and depending upon the size of the void which is created in the structure of the gas hydrate, we can have different composition of these gas hydrates, and different kinds of molecules in terms of the guest of different size can be filled up in the voids which are created by the structure of the gas hydrates. Thank you.